Ladies and gentlemen, this class recording has started. So, last Thursday, we introduced the idea of covalent bonding. First, it is still chemical bonding, which means atoms bond with each other to do what, regardless of whether it's ionic or covalent? 8 valence electrons, because that is what? A low energy state or stable. Okay? However, the difference being, right, how that occurs. Ionic bonding, we're transferring electrons from one atom to another. But covalent bonding, we're sharing electrons between atoms. We talked about this term here, a molecule, right? An electronically neutral group of atoms held together by one or more covalent bonds. If a molecule consists of atoms held together by covalent bond, what kind of elements are going to be in a molecule? Nonmetals, right? Because nonmetals covalently bond with each other. All right, what else? We talked specifically about a diatomic molecule. It is a molecule that consists of two of the same kind of atom. And then finally, we introduced the idea of a multiple bond, where a covalent bond is atoms sharing a pair of electrons. Multiple bonds consist of atoms sharing more than one pair of electrons. So a double bond is 2 pairs of electrons, 4 electrons total. Triple bond, 3 pairs of electrons, 6 electrons total. Good there? Okay. Today, we are going to start with a big fancy word that's has a lot of syllables, electronegativity. All right? So, while we talk about covalent bonding being atoms sharing electrons, a lot of times atoms don't play nice with each other. And while they are sharing, they may not share nice and evenly. And to help us figure out if that's the case, we have the electronegativity. So first, by definition, electronegativity is the ability of an atom to attract electron density to itself when joined to another atom in a chemical bond. Atoms that have high electronegativity have the greatest attraction for electrons. Atoms that have high electronegativity have a high attraction for electrons.
When you're saying most electronegative elements, are you saying like they have the greatest attraction for electrons? Is that the nuclear?
There are several factors that actually go into it,
Okay.
and we're going to talk about that in just a second here. So, here's what I want you to do. Periodic table, if you have one out, might help, okay? Based on these definitions of electronegativity, and based on what you already know about atoms, valence electrons, and what atoms are trying to accomplish, take a look at the periodic table, talk to the person next to you, and see if you guys can make a suggestion about what atom or atoms, element or elements on the periodic table have high electronegativity values. So which elements have high electronegativity values based on this definition? Discuss. Go. Maybe if your discussion partner was still doing a report last night, she'd be able to
I got everything up to this point now. It makes sense.
Come on. Critical thought. Let's go. I know, it's Friday. Critical thought's a lot of hard work. You have to think about one thing, and then think about something else, and then think about how they're the same. Ugh. It's a lot to ask on a Friday, I know. So.
No, I track my science I don't understand the definition. Greatest attraction. So the ones that want them the most. So like the second group, like group 7 and group 1.
All right, let's discuss. So, Amanda, just because we were discussing, okay? So, your suggestion as far as elements on the periodic table that have high electronegativities would be what? Okay, so groups that have 7 valence electrons. We give those a name. They're the what? They're your halogens, okay? In fact, halogens do have high electronegativity values, okay? Because what are halogens trying to do? Gain 1 electron. And if they get 1 electron, they're very stable, right? So they have high electronegativity because they are looking to attract electrons to fill that last spot and get 8, okay? Aaron, just because we, like, you know, at the end, right? The other suggestion you made would be elements in which group? The first group. And we talked about that elements in group 7, halogens, actually join together very well with elements in group 1. But that's because what happens to electrons between them? Do you want help? Do you want help? I'm sorry. What happens to electrons between group 1 and group 17? The electrons from group 1 go to group 17, right? But they don't share them, right? That's another ionic bond. That's a transfer. Here, we're talking about elements attracting electrons. Do elements in group 1 want extra electrons? No, they're trying to get rid of electrons, right? So, when we look at this chart, and I'm sorry, you guys don't have this chart. I really should probably give it to you, but I didn't. So anyway. But for now, okay, if we look at this chart, we'll see the hot zone up here in the top right, okay, things that are in red, but the cool zone down here in the bottom left, okay? Over here, if we look at electronegativity values in group 17, they are, relatively speaking, pretty high. Although 4 doesn't seem like high, we'll see in a second that that's as high as it can get. Whereas over here on the left in group 1, relatively low values, right? Under 1. Okay? Audrey, go ahead.
Why aren't the rest of the atoms in those groups that have the high electronegativity have all the same?
Okay. So Audrey's question was, how come all of the elements in group 17 don't have the same electronegativity value? Okay, that's a good question, because we've discussed that they have the same valence electrons, they should act similarly. Now, we're not necessarily just talking about how many valence electrons an atom needs to get to 8 here. While all of those atoms are trying to get to 8, okay, attracting electrons depends on having a positive charge to attract negatively charged electrons. Does that make sense? Fluorine is very small, right? It only has elements in the first shell and the second shell, right? Meaning that its nucleus is much closer to the outside of the atom than something like an iodine that has a lot of electrons between the nucleus and the very outer edge. So that's why they're not all the same electronegativity values. There are a lot of factors that go into determining how strongly an atom attracts electrons. Lucky for you, there's a guy named Linus Pauling. Okay, I know he doesn't get as much appreciation as he should probably, but anyway, Linus Pauling takes into account all of those factors that could determine how well an atom attracts electrons, and puts them all together and comes up with a scale that goes from 0 to 4. 4 being the highest electronegativity, 0 being the lowest electronegativity. And when we look at the table again, right, these elements way over here on the left, very low values because they don't attract electrons very well. But ones in group 17, fairly high values. What else do you notice on this chart? There's actually one like kind of anomaly that probably if it sticks out, if you look at it, you're like, that doesn't make sense with what I think probably should happen. Audrey, go ahead. Xenon, over here in group 18, actually has an electronegativity value, and it's actually pretty high. Okay? But xenon is in which group? Noble gases don't form atoms, or don't form compounds, right? They don't form bonds. But if we look at all the rest of them, right, they make sense because they're all zero. They shouldn't attract electrons at all. But this one does. So, long story short, okay? When we talk about these kind of patterns that exist in nature, right, usually there are some exceptions to that rule, okay? Xenon is an exception to that rule. Not that xenon is out there forming compounds with a bunch of other things. Usually it doesn't, but there are cases when it can. Now, a lot of the cases where it does, or sorry, I should say can, does is too strong. There aren't a lot of xenon compounds out there, okay? But when it does form compounds, it forms compounds with oxygen and fluorine. What do you see about the electronegativity values of oxygen and fluorine? Really high. So the only way that xenon would share electrons with another atom is if these two force it to share electrons. Does that make sense? The oxygen and fluorine have such a high electronegativity, they might, in a personification of what might happen in an interaction between xenon and fluorine, okay? Yeah, xenon, I know you have those 8 valence electrons and that you're kind of happy, but guess what? I need one to be happy, so I'm going to take one of yours. Does that make sense? So xenon might not be left, but now we like say, hey, we're going to share, right? I know you don't like sharing with many people, but you're going to share with me. You know what I'm saying? Does that make sense? Like that's... It's covalent, but xenon isn't going to share with most anybody. But fluorine is, let's say, persuasive in its techniques of getting people to share, or other atoms to share, right? Basically, it's like, yeah, I know noble gases don't usually share with people or other atoms, but guess what? You're sharing with me, all right? Now, getting back to that, okay, so, hey, getting back to something we just kind of talked about, right? Notice helium, neon, and argon, and krypton too, at least on this table, they don't have electronegativity values because being smaller atoms, those outer edge electrons aren't as far away from the nucleus. So they're held a little more tightly in helium, neon, and argon. So even though fluorine comes along and says, hey, you're going to share with me, neon says, no, I'm not, right? But it has a strong enough pull on those electrons that it doesn't.
What about
Radon is kind of weird because it's radioactive and kind of does some weird things, but, you know. And krypton actually does have, sometimes, depending on what chart you see, krypton might have an electronegativity, may not, so, yeah. Rito, go ahead. Because we find sometimes in nature that it does form compounds, and from the fact that it forms compounds with other elements, we can calculate its electronegativity. It's kind of a complex process, one you don't have to understand at this point in time, but because it does form compounds, it does have an electronegativity. But like I said, xenon isn't out there forming compounds with just anybody, right? It's got to be a special case. So, you know, it's still a noble gas, it's still unreactive, but under the right circumstances, it could form a compound. Okay? That's good. I don't know. Talk to Linus Pauling about that one. He's passed away, but... So, yeah, I don't know. All right, so what does this mean? We talk about electronegativity being the ability to attract electrons. And that's great when we're talking about a single atom. However, bonds don't happen between single atoms. Bonds have to happen between at least two atoms, right? So, we use electronegativity to discuss the type of bond that exists, but it's not just electronegativity. It is the difference between electronegativity values in bold, italics, and underlined. Do you think it's important?
A little bit.
Okay, maybe. So, let's talk about that. Okay, first I'm going to go here, and then I'm going to go here. Okay, and then I'm going to go here. Okay, good. Let's make this a little smaller. Okay, so let's talk about this bond to begin with. Okay? Oh. All right. So, this, we would give a special name. What would we call this? A diatomic molecule. It is a diatomic molecule because it is two of the same kind of atom. Now, they are both fluorine, and according to this chart, fluorine has a very high electronegativity value. But, because these are the same atom, or the same kind of atom, does one atom want electrons more than the other atom? No. They want them, or attract them, exactly the same. So even though individually they have very high electronegativity values, this one's 4.0, this one's 4.0, what's the difference between them? 0. Okay? Here is another bond that we've discussed on several occasions, right? Without using anything with electronegativity, let's finish this real quick. Without knowing anything about electronegativity, you might guess that this is what kind of a bond? Ionic, because it has a metal and a non-metal, right? There's the electronegativity values of these two. The difference between them is what?
5.
The difference is 3.1. Difference is a subtraction thing?
How did you even get 5?
I thought it was 9.
All right, so hey, there is a short homework assignment on the calendar. It's a reading thing, couple questions. We'll pick this up on Monday.